Okay, so we have another change in the program, but now Pierre Wilke is going to talk to us about the formal verification of a RISC-V processor.
That's right, thank you. So yeah, we'll talk about some work we've been doing for past few years about doing formal verification of processors. All right. Okay, so what are we going to do? Okay, so we have computer systems with software about which we prove some stuff, and ultimately this software will run on hardware, and we want this hardware to be secure too. Okay, so eventually we have to look at the hardware, so that's what we're going to do. In particular here we are going to implement and prove security properties of the hardware at the microarchitectural level, okay, so below the assembly level. How are we going to do that? We use a hardware description language, which is Kôika, which is embedded in the ROC proof assistant. In that language, we take a 32-bit RISC-V processor and implement some security mechanisms on top of it, and then we prove some properties about this. And I will show you how we do that relying on an SMT solver for automation of the proofs. Okay, let's go. So the Kôika language is, so from this paper in PLGA 20, it's a hardware description language which describes a hardware circuit, and it comes with a formally verified compiler from Kôika to Verilog, which is a more standard HDL, hardware description language. And from here you can do whatever you want. You can simulate, put that on an FPGA or even ASIC if you want to do so. So what does Kôika look like? It's a bit of an unusual language, even for hardware description language. It's consists of a set of rules, which are some components of your hardware circuit. And each of those rules either executes entirely or not at all during a single cycle. Okay, all rules are going to attempt to execute, but we'll see there are some conflicts that make that sometimes a rule is cancelled. Okay, what do those rules do? They read and they write in register. This is the storage unit in Kôika. And so a design is a set of rules that are ordered by what they call a scheduler here, the order in which the rules should appear to execute, even though it's hardware, so they will all execute in parallel. Okay. So just to precise a bit what the atomic here means that if there's a conflict between two rules, for example, they try to access, to read, or maybe more to write to the same register during the same cycle, then that's a conflict that can't happen. Okay, and the later rule, okay, the rule that does the second write to the register is cancelled entirely. Not only this write to the register, but all the effect of that rule. Okay, so that makes the semantics of Kôika quite complex and hard to reason about. So just a small example to show you this complexity here with a simple dumb circuit here with two rules, rules A and B. Okay, rules A and B who perform writes on registers R1 and R2 under some conditions. To reason about this, we need to know what the values of the registers at the end of the cycle should be, and in particular we need to know whether rule B executes or not, if there's a conflict or not. And there's a conflict in all those three conditions. Basically, there's a conflict. You can't do the read here if on R1 if there was a write here. So under condition cond 1 and etc. So for this small example, the conditions are already quite involved, and in a real processor pipeline, the conditions grow a lot more. Okay, so that's complex. So to solve that problem, we had a paper in CSF 23 where we want to do some proofs about Kôika circuits, because we have a processor and we want to do some proofs about its security. Okay, so directly on the Kôika circuit we can't do that because it's too complex. ROC takes hours to do any tactic, and it's not usable. Okay, so what we do is we compile Kôika circuit into what we call an IRR, an intermediate representation for reasoning. Okay, so basically this representation will give for each register its final value at the end of the cycle as a function of the values of the registers at the beginning of the cycles. Okay, so I give you an example here for the rules we saw earlier on for each of the two registers. So we can see in particular the final value of R2 is a big conditional and whether the rule B has a conflict or not. So it grows a lot even for a small example like that. So it's better than before because here we have all the conflict information explicitly, but it's still too large and not usable directly. So what we do is we compile this IRR further using tactics that the human prover has to use interactively so as to simplify this intermediate representation on and on until we reach a point where the representation is simple enough so that ROC tactics actually, I mean, the prover is able to perform the proof in ROC interactively. Okay. Once we have our property here, we're happy because these tactics here are verified. Well, the property holds on the IRR number n, but it also holds on the number 1 and on the Kôika circuit eventually. Okay, good. Using that methodology, we took the RISC-V processor that came with the Kôika language and extended it with a bunch of extensions, security mechanisms, and security mechanisms. So we extended this processor and this with privilege levels. Okay, our processor is able to run in a machine with the machine privilege, or very privileged, or the user privilege for processes. We had PMP, which is physical memory protection unit. So it's protection, but on physical memory. It's not an MMU. It's just an MPU. In ARM, they call that an MPU. We had the support for traps and two things related to control flow integrity, which are a shadow stack, a hardware shadow stack, and landing pads. And for each of those extensions, we do some proofs that, for example, if we have a memory access that violates the PMP, we access a memory region that we're not allowed to access, then we have an exception that's raised. Okay? Going back to how we prove stuff, actually this long chain of, okay, so here we go from 1 to n, but n could be hundreds. Okay, we could have hundreds of tactics to call, and it's a manual work and it's tedious. Okay, what we want to do is automate all this this part, because every time we change the processor, the Kôika circuit here, well, we have to at least adapt all that, and we don't want to do that. Okay, so what we do is instead we encode our problem, the IRR, into an SMT problem, and we encode the property that we prove also as a well, into the same SMT problem, and then the SMT solver does all the hard work for us, and it does it quite well. Okay, a proof where ROC took minutes maybe to just QED is solved in seconds by the SMT solver. Okay, so it's very nice to for the implementation proof cycle. Okay, it's much more interactive. Okay, good. One particular security mechanism that I want to talk about, which is work in progress, is landing pads. So someone talked about that earlier today. Landing pads are instruction to enforce some part of control flow integrity, namely the integrity of function pointers, okay, indirect jumps. Okay. So the idea is you have a specific instructions that should be present at the target of those indirect calls. Okay. So that restricts the set of valid jump targets. And this mechanism is interesting because it's really at the interface between software and hardware. It requires hardware support, okay, to well implement this landing pad instruction. So it's basically a no-op, okay. But also at the hardware level, you also need to ensure that when you do an indirect call, you actually land on a landing pad, okay. And we have that proof about the Kôika implementation. What we are doing also from the software side, we need some programs that are compiled with the support for landing pads. Okay, so we need to modify the compiler so that it introduces landing pads at the appropriate locations. Okay, so we do that in concert, and we want to prove several things about this transformation. First, that it's correct. Okay, so inserting the landing pads does not modify the semantics. Okay, so that's quite easy because the landing pad instruction is actually a no-op. Okay. But we also want to do a security proof, and that's in progress. Security proof says, well, when you do an indirect jump, you actually jump on an appropriate landing pad. Okay. I say appropriate because the landing pad may contain a label that identifies a proper landing pad for each call site, for example. Could be a different landing pad instruction. Ask me later. Okay. We also want to make our proofs more modular than they are. So far, we send the whole clock cycle to the SMT solver and ask properties about that. So we might want to do proofs for a given rule only. Okay, but if we do that, it's a bit tricky because sometimes we want if there's a rule that's in charge of a security mechanism, we need to prove also that this rule that does the security is not cancelled, actually runs. At least sometimes. Okay, so that's a challenge that we have to overcome to do that soundly. Okay. So to conclude, yeah, we have RV, which is a RISC-V processor with a bunch of security mechanisms, and we do proofs on those security mechanisms using an SMT solver. Okay, next proofs will be more modular. Oh yeah, one thing I want to mention is the RISC-V processor that we have is we don't have the proof that it's a RISC-V processor right now. It's a processor, but so what we would like to do is to prove that it actually implements the RISC-V semantics, for example, using the specification in C. Okay. And later on more security mechanisms, and we'll see which we end up doing exactly. Thank you.
Thank you. I have a question about one of the earlier slides where you added all of the IIR 1 to N.
Yeah.
Yeah, so on the slide before that, you had shown us that the logic for the conflicts was quite complicated, and I was expecting some sort of exponential complexity with the full design. Mm-hmm. And then suddenly you apply a series of automated treatments, and it's now all gone? What happened? Does the series of tactics just resolves all of the conflicts?
What is all gone?
Well, after all the tactics here on the diagram, you have proof trivial.
Yeah, because all the tactics here will do something like, if I take that, perhaps one of the tactics says, if conflict is true, then, I don't know, cond1 is always true, and we can replace some stuff.
Right, okay, great.
So the tactics are something like we can prune, okay, maybe we don't care at all about the value of R1. Oops. Uh-huh. Good. I also don't have a mic. Okay. I stepped here, if that's any useful info.
Interesting.
The tactics are something like prune, something like constant folding, and so on.
Right. So you do get to simplify away most of the complexity.
Right. Yeah.
Okay, great.
Let's see if this works.
Don't step on the cable.
What was that?
You mentioned this SAT solving step. So what kind of goals is actually offloaded to the SAT?
What kind of goals?
What kind of goals is offloaded to the SAT solver?
So the property the properties we prove here are about one cycle of the processor. Okay, given the initial state, properties about the initial state at the beginning of a cycle prove that it ends up in some state, right? So does that answer your question, or? Yeah. Okay.
Yeah, just a very small question. You're proving properties about one state, but if your precondition is sufficiently weak, doesn't that automatically lift to a safety property about traces for arbitrarily many cycles, or is there some issue with lifting that proof?
I'm not sure I got the question.
So your property is about one clock cycle.
Yeah.
But what stands in the way of having a theorem that's about n clock cycles?
So really, so the use of SMT here really applies well, because it's we encode the input-output relation of one cycle, and we can query pretty much what we want about that to the SMT solver. It's fine. If we start to have to give the model to give to the SMT solver the model of n cycles, the problem will become huge, and I'm not sure it will scale. Okay, but in the ROC part, I think we can. Discharge most of the obligations to this and the solver, and in the ROC part have a reasoning about n cycles.
Yeah, some automatically lifting of one cycle implies n cycles, right? Okay.
Why does Kôika allow possibly conflicting rules?
It's it's not an error to have a conflict, right? It can be used to model processor stalling. Okay, when you have one rule that does something, and meaning that, for example, if you write to a register, you want other rules that potentially read that register not to run for this cycle.
Right, but if I understand the semantics, it says something like you're just gonna drop the later ones. So like it sounds like in a processor like conflicts shouldn't happen, and if there is a conflict, then something is wrong with your design. Do you have to rule out conflicts as part of your?
No. Again, conflicts are part of the normal life of the processor.
Okay.
It's perhaps it's a poor choice of words naming, but no, conflicts can happen, and they happen conditionally, so they don't happen at every cycle, presumably, hopefully.
Okay, so I think we can thank Pierre again.